We are happy to have Professor Manuel Drees from Bonn University tell us about a light L mu minus L tau gauge boson for G mu minus 2 dark matter, etc. So please begin.
Thanks for the introduction. Yeah, today I want to tell you about the many things one can explain at the same time if you extend the standard model by a new one gauge group. Well, for the dark matter part, you also need to put one extra dark matter particle, not surprisingly. This is work that we have put on the archive a couple of months ago, together with my soon-to-be PhD student, Wen Bin Tao. It was actually his master's thesis mostly. And I urge you to interrupt me at any time when you have some questions. Oops. Why does this not work? Sorry, there seems to be some. Now it comes just slow. Okay, here's the content. I'll first explain what the model is all about. Then I'll describe how one can use this model to reproduce the measured value of the anomalous magnetic moment of the muon. Then I'll describe the currently strongest bound from laboratory experiments, the so-called neutrino trident events, which have been found or measured more than 30 years ago, but they still give the best bound. Then I'll describe how to incorporate dark matter. Then the next thing one can do with this model is to ease the Hubble tension a little bit by increasing the effective number of light degrees of freedom in the early universe. And there are some more additional constraints that we have looked at, which, however, turn out to be not as constraining as the ones mentioned here. And finally, this model can also be used to at least partly explain the excess of 511 keV photons from the galactic center, which have been first observed some 40 years ago or so in the 1970s. And I'll summarize. So as you surely all know, the standard model is based on the gauge group SO3 cross SO2 cross U1 hypercharge. But the reason why nature chose this particular gauge group and also why the meta representations are the way they are is basically unknown. Of course, there is one crucial criterion on the combination of gauge group and meta content, and that is that there must not be gauge anomalies. Now, it has been pointed out already 30 years ago by Hey, Joshi, and Volkas that just within the standard model meta content, Fermi content, one can extend the gauge group, in fact, by U1 factor by gauging the difference of lepton numbers, Li minus Lj. So I and J are generation indices here. Now, there's no evidence for new interactions of electrons. In fact, there are quite strong constraints from Lep, for example. So if one of these, either I or J, is an electron, then there will be strong bounds on the couplings or masses for Le minus L mu or Le minus L tau, forcing you basically into the TeV regime. On the other hand, there is evidence for new interactions of muons, namely this 4.2 standard model, standard deviation, 4.2 sigma deviation between the experiment and prediction of the anomalous dipole moment of the muon. Therefore, yeah, we'll focus here on a model, on a scenario that does produce new interactions of the muon, and as we said, we don't want to have new interactions of the electron. Therefore, then it uniquely singles out among these three possibilities the combination L mu minus L tau. The L tau part really is only there to cancel anomalies. For the phenomenology, it doesn't really play much of a role. So here's the model. It can be written down in two lines, basically. You have just the standard model Lagrangian, then you have the new gauge interactions of the standard model leptons. So the muons come with charge +1, the taus the charge -1, mu neutrinos, of course, also with charge +1. tau neutrinos with charge -1. Then you have a new field strength tensor for the new U1. So X is the new gauge boson X with 2 indices and a field strength tensor. You need the mass term for this gauge bosons. And for dark matter, we introduce a Dirac fermion psi, which has a charge q psi under the new U1 is not charged under the standard model group. And because psi is a Dirac particle at a singlet under the standard model group, for any value of q psi, the model is anomaly free. So Dirac particle means it's vector-like under the new U1 and singlet under everything else. Okay, so therefore there are only 4 parameters of relevance for the phenomenology here. One is the coupling strength, Gx, then the mass of the new gauge boson, the mass of the dark matter particle, and the charge of the dark matter particle. Of course, these last 2 parameters are only relevant for quantities affecting dark matter, not for the numerous laboratory constraints. Now, here I have not specified how to generate this mass. You could, for example, introduce a new X boson which is charged under the new U1 and not charged under the standard model. That would easily generate you such a mass and would not allow any other couplings of the X boson, except perhaps a small mixing with the standard model Higgs boson, but no fermionic couplings. Therefore, it's basically irrelevant for the phenomenology that you're doing here. Well, there's one additional term one has to consider. Now, let me go back here. When you write a Lagrangian like that, that assumes that the new U1 is orthogonal to the standard model U1. And that's in fact not an unreasonable assumption. However, once you break the gauge symmetry in the standard model, you generate masses for the fermions, also the charged leptons, and these masses are different for different leptons. Therefore, you destroy this orthogonality at the loop level. So you generate what's known as kinetic mixing through diagrams like this. A photon couples and the X boson both couple to a loop of charged leptons. These are the only particles to which both photons and X bosons couple. That adds effectively an additional term in the Lagrangian, whereby the X boson now couples to the electromagnetic current via the photon via this parameter epsilon here, which is suppressed by a loop factor. It has one electromagnetic, one new coupling, so it's EGX, this loop factor, and again, is proportional to the logarithm of the ratio of these masses. So if the masses were the same, the limit of unbroken symmetry, this would go away. But because we know that tau is heavier than mu by factor 18 or so, this is a non-vanishing contribution, and it amounts to about 1/70th of Gx numerically. Okay, so that means that effectively the psi, the dark matter particle, is really charged. The charge is precisely given by this number here times q psi, the charge of the dark matter particle under the new U1. And the same is true also for the muon and tau neutrinos. They're also really charged with charge plus minus Gx over 70 due to this loop diagram. Now, first thing we wanted to explain is the measurement of the anomalous dipole moment of the muon, and that goes very easily through this simple one loop diagram. So you have just an X boson exchange between the 2 muons. That has in fact been first calculated more than 40 years ago by Jacques Leveille. Result is given here, the simple one loop diagram. And in the 2 limits where the mass of the new gauge boson is either much larger or much smaller than the muon mass, you find that you need these values of the couplings to explain the measurement. For example, if mx is much smaller than mu, which will turn out to be the region of parameter space of relevance to us, and this term can be ignored relative to that one, the mu will cancel out, the x grad will cancel out, and you just get an integral of 2 times 1 minus x, which is 1. So this integral just becomes 1 in this limit, and you get the right size for a coupling of something like 4 times 10 to minus 4. Okay, that's the size of coupling you should keep in mind. Okay, so that fixes basically one parameter if you want to explain this measurement, one of the 4 parameters in the theory.
Manuel, I'm sorry, can I ask you a question?
Certainly.
Okay, so when you consider the mass of the X boson, you need to introduce a new Higgs boson, right? To
right,
break.
yes.
Yeah, so do you think the new Higgs boson doesn't really contribute to this diagram, for instance?
No, it does not. It cannot couple to the standard model. If it wants to, it's supposed to break the new symmetry, right? So it should be charged under the new symmetry. And then
right, L mu minus L tau, yes.
Right, so it cannot couple to, but it's a singlet on the standard model at the same time. Okay, so already the letter effect tells you that it cannot couple directly to the muons.
Okay, all right. So
Or anything else, in fact, there's no fermion coupling except through probably very tiny mixing with the standard model Higgs boson.
Right, okay.
That will be very, very small.
Thank you, please go on.
Sure. Okay, another very tight constraint comes from an old measurements in the 1980s of so-called neutrino trident events. These are events of this kind where a muon neutrino scatters off a proton and produces a mu plus mu minus pair. They're called a trident because you have 1, 2, 3 charged particles. So when you look at something like a tracking chamber or something, you have 3 tracks in there, which look a bit like this trident, I guess, and some person's imagination at least. That's why they were called trident events. And in the standard model, you have both neutral current and charge current contributions, which is why they were of interest back then as an early way to measure interference between these 2 kinds of contributions. And they were measured in the 1980s by the CHARM and CCFR experiments. And they agree with standard model within sizable uncertainties. And these measurements have been rediscovered by Prof in 2006 as a way to test new extension of the standard model by new, possibly relatively light degrees of freedom, where, excuse me, the X boson would come here, would contribute to this diagram that you could just replace the standard model Z by the X because both lines here carry muon number. Now remember, we want to have a coupling which is considerably smaller than 10 to minus 3, whereas the gauge boson of the standard model is of order 1. Nevertheless, these events have typically relatively small momentum exchange. And then, of course, for very small masses of the X boson, we would get a huge enhancement from the propagator. Therefore, even with a coupling below 10 to minus 3, this X contribution can be competitive to the contribution of the standard model Z boson. And yeah, as I said, we'll give quite strong bounds on the coupling for a given mass of the X boson. Okay, that were the strongest current constraints on just the gauge part of the model. Now let's look at dark matter. Here we don't want to do anything fancy. We just want to employ the usual thermal WIMP mechanism. So where our dark matter particle was in thermal equilibrium in the early universe, and then eventually decoupled as universe expanded. And you've probably all seen this many times. Their final prediction for the relic density of a dark matter particle scales inversely with the annihilation thermally averaged annihilation cross-section of this dark matter particle into anything else, any lighter particle. And of course, this relic density in these units, we now know to within 1% accuracy or so to be about 1/8, 0.12. Okay, so that's what we want to reproduce, which means basically we have to reproduce the right value of this annihilation cross-section. So what annihilation channels are relevant here? Well, our dark matter particle, because it's charged under the new charge, can always annihilate into anything else that's charged under L mu minus L tau. That includes in particular the mu and tau neutrinos, which are basically massless. So even for very small dark matter masses, this channel will always be open. If you have somewhat larger masses, then annihilation to charged leptons, of course, may also occur. Large leptons, mu and tau in particular, not electron. And if the dark matter mass is particles heavier than the gauge boson, then you can also have annihilation into 2 of these gauge bosons. Now, it turns out that because this P-2 forces the coupling to be very small, the annihilation of annihilation cross-section is typically too small unless one is fairly close to the resonance. So you are forced to choose dark matter masses which are not far away from half of the mass of the gauge boson. So you can employ this resonance enhancement. Okay, so this is shown here. For example, the gauge boson mass of 15 MeV, coupling of the order of the value required by G-2. Here, the green curve shows the thermally averaged annihilation cross-section, and you see it increases by many orders of magnitude when you approach the resonance at 7.5 MeV. And correspondingly, the relic density, which is this red curve, drops by several orders of magnitude. And the desired value is this blue line here, but at 0.12. You see when you're away from the resonance, you can get relic densities which are 10 or even 100 here and here. So you have to be relatively close to the pole. And there's an asymmetry here. On the side below the pole, you should be in fact like 2.5 MeV below the pole. The reason being that the freeze-out temperature, this inverse scaled XF, is this orange curve here, is still a few percent of the mass of the dark matter particle. Therefore, there is a significant kinetic energy still of these dark matter particles, which can bring even particles with a 5 or 6 MeV mass onto the resonance just through the kinetic energy. Okay, therefore, on this side, the cross-section is much smaller than when you go higher than the pole, because there additional kinetic energy will just move you even further away from the pole, obviously. Okay, that's why I also explains this asymmetry of this line. So you want to be either about 1/3 below the pole or just 1% or 2% above the pole. Now, when we try to do this calculation, we found out that MAD-DM unfortunately does not work for this model. It gave funny oscillations. Apparently, it could not handle the thermal averaging with this very narrow pole very well. So we did this ourselves and then used the method suggested by Christ and Seckel some 30 years ago to produce these results. The calculation of the relic density may not be very accurate, but even if you're 50% off, because these things changes so quickly, it just would mean that you have to readjust the dark matter mass a tiny little bit to get the correct value. That doesn't really matter for anything else. Okay, so when you're talking about thermal WIMPs, typically one nowadays has to worry about direct dark matter detection. In this model, however, this is not the case. First of all, as we will see, we will need the dark matter mass below the muon mass, so below 0.1 GeV. In that case, scattering on nuclei is not sensitive, just for kinematic reasons. Now, recently, people have started to look at scattering on electrons also. So here's the cross-section for the dark matter electron scattering. However, our dark matter particle couples to electrons only through this kinetic mixing, which is a loop effect. So this vector epsilon appears here. Therefore, the typical size of the cross-section is something like 10 to the minus 43 centimeters squared. The bound is a few times 10 to the minus 37 centimeters squared. So there are like 7 orders of magnitude in between. So there's absolutely no problem with that. And in fact, it will be pretty difficult, I think, to scale up this technology to look for dark matter electron scattering to probe this kind of cross-section. The sensor experiment is a very small thing, it's a gram scale or even less. But it's not, I don't think it's easy to scale this up to the ton scale, which you would need to bridge this gap here of this many orders of magnitude. So the next thing where our extension of the standard model might help is the Hubble tension. But first, let's talk about this effective number of light degrees of freedom, which is constrained by both the CMB and also by BBN. BBN, in particular, the helium-4 fraction, which depends on the radiation density, so basically on the Hubble parameter, which in turn depends on the total number of degrees of freedom around that have been in thermal equilibrium. So the radiation density is usually parameterized in this way. This is just the photon density plus the effective number of degrees of freedom. These factors come about because, first of all, this counts neutrinos, so it gives a 7/8, and this 4/11 arises because neutrinos decouple before the plus or minus do, and this extra entropy from the plus or minus is then dumped almost exclusively into the photons. Therefore, neutrinos are colder than photons, giving you this suppression factor here. And that's the definition of ineffective here. Okay, so defined then via the energy density. Now, in our case, if you have a light dark matter particle, or in fact also a light gauge boson, which will decay rather than annihilate, but they always lead to extra muon tau neutrinos. Now, muon tau neutrinos decouple from the electrons at a temperature of about 2.3 MeV. Okay, so this kind of annihilation to muon tau neutrinos, or also decay of the gauge bosons into muon tau neutrinos. If this happens at a temperature below this decoupling, temperature of 2.3 MeV, then it will increase ineffective. So it will produce additional muon tau neutrinos, which cannot thermalize anymore. So they just contribute extra radiation. Okay, and that will, of course, happen more, the lighter the new particles are. The more of them will annihilate or decay at temperatures below 2.3 MeV. Okay, and that gives you this, in formulas, this expression for the new contribution to an effective. So that's just a neutrino number from the standard model, plus this something which is proportional to this factor here, which, as one can see, will go away when the mass of the new particle becomes large, because in that case, it will annihilate or decay at high temperatures where the new muon tau are still in equilibrium, and then it doesn't matter. So here's the result. The green curve is the contribution to an effective just from the gauge bosons, which decay. And the orange and blue line also include the contribution from the dark matter particle for coupling value such that the relic density is reproduced for two different values of the dark matter mass. So this little r is the ratio of dark matter mass to gauge boson mass. So if the dark matter is heavier, r 0.51, somewhat above the resonance, then more of the annihilation already happens at higher temperatures where the new mu and new tau are still in equilibrium than for light dark matter. So for lighter dark matter, the constraint is stronger once you fix the X boson mass. Okay, and this bluish shaded region here, that shows the BBN constraint that an effective should be less than 3.4. Okay, and that tells you right away that the mass of the X boson certainly should be less than 10 MeV. Once you include the dark matter, in fact, you have to go to something like 20 MeV or so. Otherwise, you produce too much extra radiation. On the other hand, extra radiation is actually good from the point of view of the so-called Hubble tension. Hubble tension means that the value of today's Hubble parameter, which is extracted from CMB and other similar observations, differs somewhat, is smaller than the value that has been determined by the traditional method of this distance ladder. So here, this is shown by this plot, which is taken from the Planck 2018 paper. The best value, when you fix to the standard model value of an effective, best value of the Hubble parameter from the CMB is something like 67 or so, whereas the preferred value from the direct measurement is something like 72. And that's by now also 4 or 5 standard deviations discrepancy. On the other hand, as this plot also shows, when you assume larger values of an effective, then the CMB, through this complicated fitting of everything, actually prefers somewhat larger values of the Hubble parameter, thereby relaxing the constraint a bit. You don't get all the way to the value of 71 or 72 preferred by the direct measurements, but at least you can get to 70 or so. So thereby then relaxing it from 4 sigma to 2 sigma or something like that. So we will interpret here as an effective values between 3.2 and 3.4 as contributing significantly to relaxing the Hubble tension.
Sorry, that's kind of a pet peeve of mine. I mean, as your plot also shows, you don't only change H0, but you also change sigma 8. So your fever thermometer on the right becomes red, and that means you get into trouble with that parameter. So sure, you relax the Hubble tension, but you increase the sigma 8 tension. So unless you consider both of them together, you can't really say you've done anything.
That is true, but sigma 8 is something that particle physicists don't really trust so much, I guess, because it's some funny quantity having to do with structure formation, and yeah.
Yeah, sure. I don't understand
to
either,
understand to see how reliable that is. I mean, Hubble parameter, I think we understand by now. It's just the energy density of the universe, basically. The sigma 8 is a complicated thing, but I agree with you. But in this, if you believe this measurements of sigma 8, there's in fact also a sigma 8 tension which would go in the wrong direction. That is true. So other constraints. So I briefly mentioned already, also muon neutrinos are really charged in this scenario through this kinetic mixing, loop-induced kinetic mixing. Therefore, the scattering cross-section of muon neutrinos on nuclei will change. And the bound on this is comparable to what's slightly weaker than that from the tridents, as you will see later. Then you can also worry about collider limits. In fact, there are quite strong collider constraints from looking for 4 muon final states. So you produce a E plus or minus to a mu plus or minus, radiate X boson from there, and that one decays also into a mu plus or minus, giving you 4 muon final states at a very nice signature. And that gives stringent constraints. However, only in this mass range. First of all, the X boson has to be able to decay into 2 muons, so it must be heavier than 2 muons, heavier than 220 MeV or so. And of course, you have to be able to produce it at this low energy B factory type experiment. So the X mass must be less than 9 or 10 GeV. So both Babar and Bell published limits on that, and they are in fact pretty stringent. On the other hand, for even larger masses, you might also worry about LHC experiments, but they actually turn out, at least for the published limits, turn out to be not terribly stringent as yet. Yeah, and anyway, they would also be relevant only for very large masses. There's one more astrophysical constraint that we looked at that has to do with the cooling of white dwarfs. Now, white dwarfs are stars which are maintained not by thermal pressure, but rather by the Fermi pressure of the degenerate electrons in there, sort of a precursor of neutron stars, which are maintained by the Fermi pressure of the neutrons. But they're born very hot. At the collapse of some normal star, once it's finished its fusion. So they're born at keV temperatures at least. And then they cool off relatively quickly. And in the standard model, there are 2 cooling mechanisms. One that always works is the emission of photons, which is why we see these white dwarfs after all on the surface. That's relevant at all temperatures. However, at high temperatures, there's another channel which contributes significantly and can even dominate. And that's the plasmon decay into neutrinos. So plasmons is something like an effective massive photon that you get at high temperature inside the medium. And that can decay via an E plus or minus loop into neutrinos, because the neutrinos can escape much easier than the photons. This is relevant not only at the surface, but also in the bulk of the star. And like all weak interactions, it scales with increases with some power of the energy, so that becomes important, especially at high temperature, above a few keV, I believe. Now, people have looked at it, my colleague Herbie Dreimer and friends some years ago, and they concluded that from measurements, observations, that any new contribution to white dwarf cooling should be not bigger than the standard model neutrino emission contribution. And that leads also to an upper bound on the coupling. You notice this is not so different from the value that we wanted for G-2. So that is a not insignificant constraint here. But in fact, there is some evidence in favor of having extra contribution to the cooling of white dwarfs. Let me show you a plot from this paper by Eisner et al. From 3 years ago. So what's shown here is the number density distribution on the logarithmic scale of some populations of white dwarfs. It had 3 different populations in different places as a function of what's called the bolometric magnitude. Now remember that for astronomers, a smaller magnitude means brighter, hence hotter. So the hottest stars are at this end of the distribution, where because they cool off relatively quickly, there are not so many of them around, whereas the colder ones are over here. Now this black curve here is what you would predict from stellar modeling, and this distribution should look like with just standard cooling mechanisms. And you see that you a bit over predict here the abundance of hot classes of hot white dwarfs. Here in this plot is perhaps better to see in this population. Therefore, in this paper, here by Eisner et al., they added some extra cooling mechanism with 2 different sizes, the blue and red. The red fits perfectly over here, but maybe exaggerates this peak at low temperatures a little bit, and the blue is somewhere in between. Now, the extra cooling that they included is from axions, so it cannot be directly translated into our scenario because the temperature dependence is also a bit different than in our scenario. But nevertheless, at least there is some indication that indeed some extra cooling mechanism for white dwarfs might be preferred. Now, the last thing I want to discuss is the annihilation of our dark matter particle into the plus or minus pairs in the relatively late universe. Now, this, of course, again, requires this kinetic mixing with the photon of the X boson. Therefore, the annihilation cross-section into E plus or minus is about 2 × 10⁻⁵ smaller than the one into neutrinos. Okay, this is the one that sets the relic density. So normally you would say that this one is completely negligible because of this 2 × 10⁻⁵ factor. However, this need not be the case. Remember, we want to be in the vicinity of the resonance. So m psi should not be too far away from half of mx. Now, if you are below the resonance, then we saw the relic density is obtained correctly, largely because of the kinetic energy that the psi particles have in the early universe, which can push them onto the resonance. However, of course, the kinetic energy decreases as the universe cools off. So the annihilation cross-section after thermal averaging actually decreases when the universe cools off. So in that case, indeed, it would be completely negligible. On the other hand, when you go just above the resonance, then kinetic energy moves you away from the resonance. So cooling off actually increases the cross-section. So at that point, the second point that you could choose to get the right relic density, today's annihilation cross-section is in fact considerably larger than the one in the early universe. Okay. In that case, this contribution may still be sizable. So this is relevant only if you are on the far side of the resonance. Now, this is also constrained by the cosmic microwave background, because this channel would dump energy into the universe, which interacts with everything else, and in particular would increase the early ionization fraction, and therefore the optical depth for the CMB photons, which is one of the parameters usually not so much of interest for particle physicists, that's also fitted in by Planck and the other CMB experiments. And from that, you can derive an upper bound on the annihilation cross-section. into E plus E minus, thermally averaged, which is about 0.03 femtobarn and scales linearly with dark matter mass. So why the scaling? First of all, the probability to meet is proportional, or the annihilation rate is proportional to the square of the number density of your dark matter particles always. It's just what you have also in the indirect dark matter detection. And the number density is inversely proportional. It's proportional to the mass density divided by the mass, and what's fixed by omega is the mass density. So if you have a larger mass and the same omega, it means you have a smaller number density. Okay, that means that you could allow a larger cross-section for a larger mass. And in fact, because of this n squared scaling, they would normally even scale like m squared here, the bound on the cross-section. However, what matters here is not just the event rate, but the energy dumped into the early universe. And that, of course, increases linearly with the mass of the dark matter particle, therefore removing one of the two factors. Therefore, this one scales only linearly in the dark matter mass. On the other hand, if you want to explain this long-standing excess of 511 keV photons from the galactic center, then the cross-section you need scales quadratically with the dark matter mass, because here the idea is that you produce positrons with a mass, initial energy of maybe a few MeV, which cool down before they then form bound states, positron bound states, and annihilate. Okay, that's what this 511 keV photons obviously are from annihilation of positronium, more or less at rest. Okay, and in that case, for that source, is really only the number of positrons that matters. Therefore, you have this m squared scaling. And to get these two into agreement, in fact, you want to be at as small a mass as possible to satisfy that one without violating the constraint. But however, we saw already that we needed at least a mass of 10 MeV or so in order not to overproduce an effective. And if your mass is 10 MeV, then in fact there is an additional constraint that tells you that really at most 50% of the required E plus positrons to explain this excess of 511 keV photons can come from dark matter annihilation. Otherwise, you have too many MeV photons, because the positrons, when they're produced at several MeV, do have a finite probability to annihilate before they are slowed down. And that will then produce MeV-ish photons, and in that energy band, there is no excess, as has been pointed out by Beacom et al. Some already 15 years or so ago. Therefore, we cannot really, because we are forced to have at least 10 MeV dark matter particles, we cannot really explain all of this excess, but perhaps some of it. And because of this bound up here, we would have to appeal to a relatively strongly peaked dark matter distribution in the galactic center to get a significant contribution. But every little thing helps. So here's now our final money plot. If you want, let me walk you through these various bands. First, this light green region, that's where you want to be. So this is the mass of the new gauge boson and the coupling. This light green region is where you want to be in order to get the right value of the dipole moment of the muon, but a few times 10 to minus 4 for very small masses, and then this scales linearly with the mass as we saw for masses larger than the muon mass. Then this gray region is definitely excluded from the CMB constraint, because here the psi particles can also annihilate into muons, and muons do dump a significant amount of energy into the plasma, thermal plasma, so that would definitely not be allowed. Remember that electrons, the annihilation cross-section to electrons is suppressed by the Zoop factor, but for the muons is not suppressed. So that's clearly excluded. On the other hand, this purple region is excluded by this BBN constraint on N effective. The small blue region is the one where N effective is between 3.2 and 3.4, so where we say that you can help something with the Hubble tension. Now, these various colored lines, first of all, the blue one and this orange one, these are lines giving you the right relic density for a dark matter charge of 1 and a mass which is 51% or 50.1% of the mass of the gauge boson. If you're closer to the pole, this orange line, you need smaller coupling, of course. If you're a bit further from the pole, you need a bit larger coupling. And the star finally is sort of our optimal choice, which can give you also some significant contribution, significant flux of 511 keV photons, at least for sufficiently strongly peaked dark matter distribution. Now here the other constraints, the green line is the one from the coherent neutrino scattering. So that's a bit weaker than the where is it? The red line, which is the trident bound. Okay, that's a bit stronger here. Although in this range, they are really almost the same. For the coherent bound becomes weaker at larger masses because it has a even smaller momentum exchange typically than these trident events. And the black line is the white dwarf cooling. It's a little bit weaker than the others, but also not so far away. And yeah, over here then are these collider constraints. This is the one from Babar, but again, it kicks in only for X boson masses above twice the muon mass. Okay, now here's what happens when you allow the dark matter charge to deviate from 1. This black line is this is now in the plane of the dark matter charge, and delta, where delta parameterizes how far you are above the resonance. So small delta means you're very close to the resonance. Larger delta means you're a bit further away. So of course, for U1, really what matters is the product of charge and coupling. So when you're further away from the resonance, you can compensate this by increasing the dark matter charge. So that's why this curve has a slope going up. Now this red region is again excluded, in this case by the CMB constraint. The green is where you can make a significant contribution to the 511 keV photon flux. And the slopes of the red and green are basically the same because that is all at times where the kinetic energy is negligible relative to the mass splitting. The distance, the propagator is really already dominated by this delta, even though delta is pretty small, rather than by the kinetic energy. Whereas in the early universe, the kinetic energy is significant. That's why the slope of this line differs from the slope of this boundary of the red and green region. And you find here that the optimal choice would have a charge of like 1.5 or 2 or so. That's not unusual, not reasonable, I would say. Yeah, we also make some predictions, further tests of the model. First of all, especially if you want to explain the this 511 keV photons or make a significant contribution there, that really means they need a sizable annihilation cross-section into neutrinos. Then it's in fact more like 10 to minus 25 here rather than 24 rather than 10 to minus 25. But even in the other case, you still have significant annihilation cross-section into neutrinos. And that's quite easily testable, for example, at the upcoming Juno experiment via elastic neutrino electron scattering. So that should be relatively easy to see. It has actually also been pointed out by these people here that, in fact, for coincidentally the same region of parameter space, you get a slightly improved description of ice cube data because the resonant scattering or annihilation of high energy incoming muon neutrinos on the relic muon neutrinos, they change the flavor composition a little bit. And at least according to that paper here, that improves the description of the ice cube data somewhat. But it's not a very strong effect, statistically speaking, but another hint. Finally, we predict for our best fit point that we have something like 250 events with a single photon at center of mass where in the center of mass energy, the energy of the photon is basically just 1/2 root s at Bell 2 over their full luminosity, and a similar number if somebody builds a tau charm factory with luminosity of something like 2 atomic inverse per year, which is something that physicists in China apparently are thinking about. To see that, of course, you need a single photon trigger, which currently does not exist in Bell, as far as I know. So the diagram is the one shown here, just emit a photon and emit an X boson, which again couples two electrons only through this kinetic mixing, which is why this number is so small, and which is why you need Bell 2 really to produce significant event numbers. And the whole Bell data set, you have only 5 or so. But Bell 2 is supposed to have much higher luminosity, of course. I guess they're still struggling a little bit, but let's hope that they get this fixed at some point. Plus, Bell 1 also didn't have a single photon trigger. Okay, so here's my summary. I hope I convinced you that this quite simple extension of the standard model by a new anomaly-free gauge group gauging the difference of lepton numbers L mu minus L tau with the mass scale at 10 MeV for the dark matter, 20 MeV for the gauge boson, a coupling of 4 or 5 times 10 to minus 4 dark matter charge of order 1. With that I can explain rather a lot of things. I can produce thermal dark matter of the desired relic density. I can explain G minus 2. These two things I can explain spot on. I can ease the Hubble tension with perhaps more problems with the sigma 8. And I can make a contribution to the flux of 511 keV photons. And that can be tested by future neutrino experiments. Juno, also coherent experiment, is supposed to become more sensitive. So if they can increase the sensitivity of the coupling by another factor of 3 or so, and they should also be able to see this. And possible future high luminosity or current, even if they achieve the high luminosity E plus and minus colliders if they have a single photon trigger. Okay, that's all I wanted to tell you today.
Okay, thank you very much for the nice talk. Are there questions or comments?
What about all the ratios RK star and the like? Don't people employ L mu minus L tau also for these?
You mean for the BD case? Well, yeah. There is an argument for extra muon interactions. However, to do that by itself, it doesn't help you anything, because that would be a very tiny loop effect only. So you have to also couple it to B quarks somehow, and not just by this kinetic mixing, that's much too small. So yeah, people also mention this sometimes, but to make this work, you have to add quite a lot of other stuff. And then you also have to worry about a lot of other constraints. So I'm not so sure whether that really is helpful for this purpose, at least for this parameter range. I think this coupling is anyway too small to make a significant contribution there.
I have one very naive question concerning, I think on page 14, you showed the collider bounds. And you said that you have bounds from Barbar and Bell from E plus E minus to form muons. Now, in principle, you could also have a decay of your new gauge boson to neutrinos. So you would get E plus E minus to muons and missing energy, or even E plus E minus to E plus E minus plus missing energy. Do you know whether there are any experiments or any bounds from low energy E plus E minus experiments looking for MET?
I don't think so.
Well, actually, my group has done that analysis for muon and also 2 mu plus missing energies, and we could set a similar bound from the Bell experiment. Yeah, we can talk.
I see. Is that published?
Yeah, it is published.
Okay.
I can let you know. Yeah.
Sorry, I guess you missed that.
Mhm.
Yeah, that would be nice because it should extend to lower masses also, in principle.
That's right, yeah.
But of course, yeah, for us also lower masses means even smaller couplings for the relevant to be to explain G-2 and so on. That will make it experimentally even harder. I guess for experimenters didn't look at it evidently they did, but it's a bit more difficult, of course, to look at because you look at you're interested in very small rates, and then you have to worry about your experiment not missing some energy, which is really there in cracks and so on.
Yeah, right.
Also, for theorists, not easy to model, of course. But if there's a real experimental analysis, I would definitely be interested in seeing that. Thank you for pointing this out. But yeah, the other question for E plus or minus final state, that would certainly not be a good idea for this. Would certainly be much worse limit than for the muon final state because you always get this extra loop factor to couple this hour gauge boson to electrons. So
yes, sorry.
That's always a much weaker constraint. And that's also why these dark photon searches are probably not the best way to probe this here.
So, Emmanuel. So, yeah, so in one slide, you showed the lepton dark matter scattering cross section, which is about 10 to minus 44 centimeters square. So, for neutrino dark matter scattering, it should be the same, right?
Neutrino electron scattering, you mean?
No, neutrino dark matter scattering.
No, that will be much larger.
Much larger than this.
Both, at least for muon and tau neutrinos, will be much larger. For electron neutrinos will be about the same, yeah. But muon and tau neutrinos, you don't need the loop factor, right? They are charged under our U1.
Okay, so that's the 10 to 5 factor you mentioned. So that, as you mentioned, it's much, it's larger by about 10 to 5.
Sorry?
So it's larger about 10 to 5, roughly. I mean,
that was for annihilation cross section, but it should probably both for the
probably scale.
should probably
anyway.
be.
I mean, the reason I'm asking is that from cosmology, there is a bound on neutrino dark matter cross section.
Yeah, we looked at that, but that was still quite far away.
Oh, okay, good. Okay,
for this mass range.
Yeah, I was calculating that, but okay, good. Very good. Thanks.
Could you move to page 21 for the E plus E minus collider thing?
Excuse me?
Could you move to page 21 for
page
the E plus E minus thing? Yeah.
This one?
So, yeah. So I'm more concerned about the background. Is there any kinematic feature that can distinguish this particular signal to any other mundane background?
Like I said, in the center of mass frame, it's a line, basically, because the X boson mass is much smaller than nanostorm S, and then the energy of this photon is just 1/2 root S.
I see. Okay.
It's a fixed line you would look at that should stick out of your backgrounds.
So
physics background is very small.
Okay.
Physics background would be photon plus neutrino production, which would be small and not a line. But yeah, the main background, there was recently a Barbar paper on this, in fact, which I looked at. Main background was from 2 photon events where 1 photon somehow gets lost. It's not likely to happen, but you're talking about very small cross sections here after all. So
then it can also be searched at the Tau-Chan factory.
Yeah. Since our X mass is only 20 MeV or so, you don't.
Okay.
In fact, the physics background becomes, well, the cross section becomes bigger, single cross section becomes bigger. The physics background becomes even smaller because there's a weak interaction.
Yeah.
The instrumental background, of course, that depends strongly on how the detector is built, cracks and coverage efficiencies.
Thank you.
Are there other questions or comments? Okay, if it is not the case, then we may thank Professor Drees again. Thank you.
Thanks for the invitation again.
Okay, thank you very much.
Thank you very much.
Okay, bye.
Bye-bye.
Bye bye.